Let f of x be defined as 2 minus cos of 3 over x times absolute value of x when x is not 0, and 0 if x is 0. We want to know, is f differentiable at 0, why or why not? And we'll show our work. So we have already proved that this function, or a function like this, is continuous. Okay, so we know it's continuous. And the way that we proved that is by the squeeze theorem, or the sandwich theorem. So yep, so it's continuous. However, continuous does not mean that it's differentiable. So actually differentiability implies continuity, but continuity does not imply differentiability. Okay, so we don't know anything about differentiability. And what differentiability means is it means that the derivative is continuous. Okay, so differentiability means that the derivative is continuous. So really what we want to find, we want to see if the derivative is continuous everywhere. That means, does the derivative exist everywhere? And to do that, we're going to use the limit definition of the derivative, or the difference quotient definition of the derivative. And really, the point that we need to check is this point that could be a discontinuity, the point 0. Okay, so that's the point we're going to check. Before we do that, let's think about what the graph looks like here. And just to understand really what's happening to this graph, let's look at 3 different graphs. First, cos of x. So this is just the regular periodic function. Cosine looks like this, and like this. Okay, there's our cosine function. And really the thing that's causing issues in this function that we're given, that we're trying to decide if it's differentiable, is this 3 over x piece. So let's think about why some error is happening there as we're looking at x going to 0. Like, why do we have to have this separate point as we're looking at 0? So if we're looking at what's happening as x is getting close to 0, that inside of the function 3 over x, or in this example 1 over x, that's getting close to infinity. So really we're kind of looking at, so as x is getting close to 0, we're looking at cosine of infinity, even though we can't really think about that. Okay, cosine of infinity, and that means that the period of cosine keeps shortening as we get closer and closer to 0. So we end up with a function that kind of looks normal out here, but then as we're getting closer to 0, the period is just kind of getting irregular. The period of cosine is like scrunching up like a spring, where we can't really see what's happening as we get close to 0. And the same thing on the other side. So we have normal cosine, and then all of a sudden, because of this division by 0, we're getting close to infinity, and the period is shortening like that. So that's why we have this kind of irregular cosine graph. So now what does the 1 over x have to do, what does this absolute value in front here, what does that do to the cosine x? Well, as x is approaching 0, this piece in front is approaching 0. So this absolute value is approaching 0, so it's pulling this strange cosine 1 over x function down. So what we end up with is more a graph that looks like this. Like it's still having that kind of strange like period that shrinks as we get close to 0, but the absolute value of x pulls the graph down, like this. So the limit of this function by the sandwich theorem ends up being 0, so that's why it's continuous, but the limit itself, or the derivative, is not continuous. Okay, so now let's look at that. So now hopefully you have an understanding of kind of what's happening here. Like this 1 over x or 3 over x inside the cosine is causing this change in the period, this compression at 0, and we don't know exactly how far it's compressing because our inside value of the cosine is approaching infinity. But the absolute value of x pulls the limit down to 0. However, it still is going to be impossible for us to see what the derivative is. Okay, so now let's look at the definition of the derivative. Okay, so the definition of the derivative is, we're looking at the limit as h goes to 0 of f of x plus h minus f of x over h. And really the part that we care about for the continuity of the derivative is this point right here, so 0. So we're only going to look at f of 0. Okay, so let's plug x equals 0 into this limit definition. That's going to be the limit as h goes to 0 of f of 0 plus h, so f of h, minus f of 0 over h. So we just plugged in 0 for x. Okay, so this is going to be f of h limit as h goes to 0 of f of h minus f of 0. Well, we know that is just 0, so that's going to be 0. So limit h goes to 0 of f of h over h. Okay. And now we're looking at a limit, so we're thinking that h is not 0, so let's plug in this function with h. So f of h into this right here. Okay. Limit as h goes to 0 of 2 minus the cosine of 3 over h times the absolute value of h over h. Okay, now let's look at what happens to the absolute value of h. Okay, the absolute value of h is just h if h is greater than or equal to 0, and its opposite h if h is less than 0. So think about if we plug in like -2 here. Absolute value of -2 is 2, which is -2, positive 2. So that's how this definition of absolute value comes about. Okay, so now let's split this into two limits. Let's look at the right hand and the left hand limit here. Okay, so the limit as h goes to 0 from the positive, from the right. Well, if we're looking at the positive values, we can replace h, absolute value of h, with just h. So that would be 2 minus cosine of 3 over h times h over h. And then those h's are going to cancel out, and we get the limit as h goes to 0 from the positive of 2 minus cosine of 3 over h. Okay, now let's look at the left-hand limit. The limit as h goes to 0 from the negative. That's going to be 2 minus cosine of 3 over h. And then if we're looking at the negative values, that means the absolute value of h is negative h. So times negative h over h, which is going to be the limit as h goes to 0 from the negatives of 2 minus cosine of 3 over h. And then negative h over h is negative 1, so times negative 1. Okay, so looking at both these right and left-hand limits, if you think about those graphs that I drew earlier, there's now nothing pulling down these cosine graphs. So what that means is that these graphs of this limit, so of this derivative function, the graph of the derivative as we get close to 0 is just doing this. And there's nothing pulling it down to 0, so that limit does not exist. So yeah, so this limit here, as well as this limit here, both of those limits do not exist because there's nothing pulling the cosine 3 over h graph down to 0. That's kind of the reasoning behind it. To do like a formal, rigorous proof, you really need some like real analysis, but kind of the idea is that no matter what value close to 0 you're looking at, so like this is really, really close to 0, you can always find a spot past that closer to 0 where the graph is up here or down here. So you can never say that it's going to keep getting closer and closer to 0 because it's always going to have another loop after that. It's going to have another full period of the graph between whatever close point you choose and 0. So this limit does not exist. And that means that the graph is not, or that equation, f of x, is not differentiable. Okay, so it's not a differentiable function, even though it's continuous. So continuity does not imply differentiability. And we can't use the squeeze theorem here because there's nothing to squeeze this between.